Okay, lecture 17C, transition function, attention now. Two manifolds, then I use partial derivative instead of this here, okay? There is no mapping, okay? There is no mapping and no mapping. It's just functions, okay? Which relate one set of variables to another one. Now, first of all, we will express the relation between points using partial derivative in the context of two overlapping charts on a manifold M and the corresponding mapping to another manifold M3. As I said, you see, there is no this linear mapping here, only function. Now, step 1, coordinate system and mappings, manifold M3. You see this chart here, you see the coordinate is called xi, I is equal 1, 2, 3, because we are using the dimension 3. Likewise, in this case, let's put u of y with this coordinates yi, I is equal 1, 2, 3. Attention now, okay? This case, the transition function, this must be given. yj function of the, in this case, the coordinates xi. I is equal 1, 2, 3. So this transformation is valid only in the intersection of ux and ui. So the relation here, don't forget that. You see, this is here, this is xi and yj on the same point P. Attention now. See, that's a very important. And this relation here, you see, look why I wrote, you see, the transformation is valid only in the intersection. Because in the intersection is a place which I can relate the coordinates of point P, xi, with another coordinate yj at the same point. That's important here, okay? So that's why this point has to satisfy to the coordinate xi as well as, in this case, yj. That's why in this intersection region, I can write down the yj in terms of xi. You see? Then here, this I said, y must be in the intersection. Now, this analogous, then we'll do for the manifold M3. Okay, instead of u sub x and u sub y, the notation is v sub mi with the coordinates, you see, mu alpha. Alpha is 1, 2, 3. Likewise, the region v ni with the coordinates ni beta, beta 1, 2, 3. The same analogous to the xi and yi. You see? Now, the transition function between these charts, okay? You see, ni beta function, this is valid only on this intersection here. This is valid only on this point over here, on the red mark. Now, function f, mapping the manifold M to the manifold N. F takes a point P, belong to M, then in this case, the transformation to point Q belongs to N. So I must know the relation mu alpha in terms of xi, that is x1, x2, and x3. Likewise, you see the relation between these coordinates, okay, with the coordinate yi, this is a function g. G behaves exactly in the same way as F. So, step 2, I like to mark here, just to, this is step 1, over here, see? Now step 2, Jacobian. You see, Jacobian involves partial derivative. So, Jacobian of coordinate transformation. 1, see 1 here. Jacobian of the, in this case, of the transition map between charts on M3, only on M3. We know that on M3, at any point over here, can be represented in 2 different coordinates. You see, coordinates xi and yj. That's why I can obtain the Jacobian partial derivative yj xi. Attention now, j and I is free indices, so you're gonna have 9 components, okay? 9 components. J is equal 1 to 3, I is equal 1 to 3. So this describes how coordinates change between ux and u sub I. Again, the points which I'm computing the Jacobian must be in the intersection between ux and ui. That's a location where I can write a function yj in terms of xi. Okay? Even for point P, okay, I'm talking about region. Here it's about region. See? Now, likewise, partial of me alpha xi describes how the function f maps from M3 to N. See? This relation must be known. Okay? We have to know the relation just to get the Jacobian. Okay? We say, again, we have nine components of this second order tensor. See? Likewise, partial of ni beta respect to yi describes how, in this case, the function g maps from M3 to N3. You see? Attention now, nu belongs to n, y belongs to m. You see? That's so. Now the chain rule, just substitution here, since xy and yj, in this case, describe the same point. Attention now, okay? When I have a point over here, any point in this region, okay, this point can be represented by xi or yj. See, that's what is saying here, okay? See, since xi and yj describe the same point in M3, okay, then I can have this chain rule over here, okay? Now, you see, alpha I, attention now, alpha I, it's free, you see? Alpha I is free, okay? And in this case, the other index are dummy, okay? Similar for this one, okay? The same I do here, the same I write there, okay? So you get the full composition by substitution. So partial of these coordinates, again, with respect to xi, you see, look at here. This one here is the same as this. And partial of me, the alpha in this case, you see, this is partial of xi. You find here xi over here. You see xi over here, xi over here. This one and this one. And then this alpha and alpha, dummy. This is j and j, dummy. So then by composing, okay, this partial derivative, I can obtain any relation that I want. See? That's why on the previous lectures, 17 B17A, you just work with the linear mapping. You substitute this linear mapping, okay, with the functions. That's the functions. That's why you have a partial derivative just linking, or say, those variables. Okay, this is very, very, very important. Okay, relation here on the study of manifold. Okay.